working with a fixed n. We let n tend to infinity now. It's about the time? Yes. Okay. Good. So we look at this question of a limiting distribution for arithmetic function, and then we'll start additive business. Okay? So 3.1 is distribution function. Of a real, so now we are definitely looking only at real arithmetic function. Okay, so we look at real arithmetic function, f, be a real arithmetic function, and we look at its empirical distribution first. So the empirical distribution the following, you do the following, you look at this distribution depends on n, you truncate at n, you look at the first n elements, and you look at a real number u, and this is just 1 over n, and you look at the cardinality, boom, 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 at the cardinality of n up to capital N, for which f of n is at most u. So this is fine. You look the proportion of the number for which you have something like that. We saw something of the kind this morning. You know, sigma n over n is at most 1/2, and we try to, or at most 2, and then we go to the limit and we see how it is. Okay. So in some way, this is the distribution function which is associated to a measure. If you want to see it as a measure, it is associated to the measure which is 1 over n, summation n up to n of direct measure at the point f of n. Because if you see, if you are looking at what is the measure of the interval minus infinity to u with respect to this measure, you get exactly that. This is, if you wish now, this you can see it as being nu n f of the interval minus infinity to u, and so it is a distribution, the distribution of a probability measure. Okay? As we are used to. So now the point is to try to see what happens when n is tending to infinity. Okay? So at least something that could be a good case is when there is a limit when n tends to infinity. Okay? But there may be some curious phenomenon appearing. So we look at the limit of f, so this depends on f and n of u when n tends to infinity. And we assume that it exists. If it doesn't exist, we are done. We said there is no limit. Then the limit, you can find it in a different way. You can find it with a logarithmic measure or something like that, but we're just looking at this, and we look at that. So we assume it exists. So what can be the pathologies? The pathologies may be that all that tends to 0. Okay? For example, if you take the function omega of n from some point, except of course you will have always some element for which omega of n is small, if you have a prime number. product of finite number of prime, bounded number of prime, it will be finite, but usually you know that it will tend to log n. So this is not very nice. So what you would like to have is something which is, in any case, that the good case, at least, let us say good case, require at least that ff of n as tends to, let us say, ff with something which is that. So it's clear that limit ff, capital FF, will be something which is non-decreasing. Work a bit, you have something which is pointwise convergence of something which is non-decreasing. What you get is also something which is non-decreasing. This is okay. So this is non-decreasing. And what we ask for is that with limit when u is tending to minus infinity of f of u is equal to 0, and you don't want to have too many elements which are tending to minus infinity. You see, if everybody is tending to infinity, this limit will be 1. And limit when u is tending to plus infinity of ff of u is equal to 1. So you don't lose too many elements. Of course, if you assume that your arithmetic function is bounded, then this will be the case. But we don't ask neither that it is bounded. There may be some large values, but not too many. Okay, not too many going to plus infinity. This will be something of a set of density 0 if it tends to infinity, and the same thing for minus infinity. You may have some large values, but not many. So this is what you assume. So if you're in this condition, you have something which looks like a nice distribution function, except that there is still one little point. Yes, you want something to be continuous from the right. So let us, we saw in the morning some example of this kind. So let us consider, as an example, f of n. I don't ask anything about arithmetic property that it is additive or anything like that. I just ask what it is. Okay, let us say I take f of n is 1 plus 1 over n. Okay, so it has a nice limit distribution, and I don't make this, you can work it. We saw already some example, and otherwise you do it by yourself. You will see that the limit is something which is, okay, if you are less than 1, or at most 1, it's okay. You have nobody, so the limit will be 0. Okay? But if you have something which is larger than 1, then you will get almost everybody, and so it will be 1, except that if you take the value exactly at 1, the value exactly at 1 will be something which is 0. You have nobody which is at most 1. All the values are larger than 1. So if you look at the ff will be the following, is the following function. It is a function where you have 0 up to this value 1, and here you start to have something, and here you have something which is, no, including 1, it is 0, and only starting from 1, it is here, and it's not continuous from the right. Okay? So is it bad? Isn't it bad? We'll see that it's not really bad. And what is important is more, you see, we have two ways for the time being to look at a measure. We can measure it and look at the distribution function. We know also that we can integrate any function which is bounded and continuous on R with a probability measure. We can integrate anything like that. So we can see also a measure as being a linear form over the functions which are continuous. They can be, how to say, they can be complex valued. This is not the problem. The problem is that they are defined on R. Okay? So we are now dealing with something. I don't want to make all this business, but just to say that now we have definitely to say something about what is the convergence of probability measures on R. Okay? So I don't want to spend too much time on that. So I will call that weak convergence of probability measures on R. This is what we want to do. Okay. First of all, one point is that this weak convergence is definitely something which is in the vocabulary of probability. I think it would be, if you are on the side of a functional analysis, you would rather say something like close convergence, convergence étroite. Okay, but this is used in probability theory, this vocabulary of something to say that it is a weak convergence. So, okay, definition. So, definition. So, first definition will be the following, that, okay, we say that a sequence of probability measures mu n converges weakly to a probability measure mu if for any f which is continuous and bounded on R with value in R or C, whatever you wish, is the same thing. By linearity, it's not a big problem. You have the integral of f d mu n converges to the integral of f d mu. Okay? So this is fine. This is the definition. And we say, of course, that mu n converges weakly, full stop, if there exists mu, a probability measure such that mu n converges weakly to mu, and you can see that there is unicity. Okay, I don't want to say too much. And then we write, the notation usually is to say something like that, mu n weakly converges to mu. You are going to tell me that this symbol has been already used somewhere, but essentially there is no risk to get confused with the implication. Okay, so this is what you want. Okay, so now we'll go to okay. So now we would like to express that in terms of the distribution function, because we know that we like to see the probability measures in terms of the distribution function. Okay? So you have the following proposition. It's not that difficult, all that. You have the following, that the sequence of probability measure measures mu n converges weakly towards the probability measure mu if and only if you have the following, that f mu n, you know what this is? This is the distribution function associated with mu n. Okay? If this tends simply pointwise, do you say simply or do you say pointwise? Pointwise better. To f mu, and you know that this is not good to, it's not a sequence, it's just f mu. You know that this doesn't work exactly, but indeed it will converge pointwise at each point where the limit is continuous. Okay? And you know that the point of discontinuity, since it is a non-decreasing function, you have only countably many of them, and at each point it is regular, it has a limit from the right and the limit from the left. So then you can always make out of such a function which is continuous from the right without changing anything almost. Okay? So tends pointwise to theorem at each point where f mu, it has to do with the limit, where f mu is continuous. Okay? And indeed you will have the same thing. I'm not going to write it. It's that if you have a sequence of probability measure mu n, that f mu n tends pointwise to a distribution function at each point where it is continuous, then you have mu n which converges weakly to the measure associated to this distribution function. Should I write it also? No, it's okay. So definitely you can find out whether it converges in terms of distribution functions. Okay? Good. Then there is also another point that instead, as you know, instead of integrating all the bounded continuous function, you may have a certain subset of this which is enough, which is dense in some way, so that if it is true on this set of function, it will be true for all bounded continuous function. I'm not going to prove it, but essentially what you use is the imaginary exponentials. Imaginary exponentials are very nice continuous functions. They are bounded by 1. The modulus is always equal to 1. So they are nicely bounded. And if you have convergence on this subset, it will be enough to have convergence everywhere and to be in this case. So I will introduce something. There is some special wording for that, for this Fourier transform. You see, probability has been developed before there was this formalism in terms of measure that has been introduced by Kolmogorov in around 1930. Probability existed, and so they had their own vocabulary for that. And so this is what is called, so I am in 3-2, I stay here. 3-3, so characteristic function, a sub-paragraph of this one, section of this one, characteristic functions and Levy's theorem. So this is the third characterization, which is the following. So let us give first the definition of the characteristic function. let mu be a probability measure on R, then its characteristic function phi mu is the function from R to C, which associates to each real number t the quantity. So what you are doing is simply you are integrating the function exponential I t x d mu x. So what you can think of is just, you know what is this integral, because we're on R. So to mu you can associate its distribution function, and you are taking the Riemann-Stieltjes integral. So there is nothing really too bad. The meaning of this means simply that here you have two variables, you don't know which function it is. So t is a parameter, is fixed, and what is the function is the function with to x do that. So in some way, if you want to understand what I mean is the function that is to x, I associate e to the I t x, and then I integrate it with respect to the mu function, if you don't like the d mu of x. Okay, this is a function, complex valued function from a real argument, and as such you can integrate it with respect to mu. This is just a convenient notation. Okay. So why is it called characteristic? Because if two measures of the same characteristic function, they are equal. This is why it is called characteristic. It is a characterization of the function, of the mu function. Okay? So the correspondence, I don't even write it, the correspondence between mu and in some way phi mu, if I can write it like that, is a bijection. Why? Because you have Fourier inverse. So you can go back that to Fourier inverse. You will have the following: phi mu, f mu of t plus h. I am not going to prove it, but to do it like that, minus f of t is equal to the limit when t tends to infinity of 1 over 2 pi, the integral from minus t to plus t, of symmetric integral, of course, of e to the minus ETH divided by IT, I to minus ITX d phi mu, phi mu of x, phi mu of x dx. Sorry? I put too many t's around. Sorry, I will correct that. Here, it's not necessary, and then if you put it here in the inverse Fourier. Oh, you put it there? Yeah, you put it there. Yeah, just the same thing, you can consider it. Usually it is defined that way. There are too many t and x. What is it? X? No, it's fine. Yeah, phi of x dx. Okay, so this is the inverse Fourier transform. But essentially, you think in your mind that this is characteristic. If you know what is the Fourier transform, you know what is the distribution itself, what is the measure itself, probability measure itself. So this is why you have this unicity. And you have some nice property of the characteristic function that it is continuous, it is uniformly continuous, it has very nice property. Uniformly continuous function with values, of course, in the unit circle, and phi of 0 in the unit disk, and phi of 0 is equal to 0. Okay? Phi of 0 is equal to 1. It is the complete mass, of course. If this is 0, you are just integrating that and you get 1. Now, what is Levy theorem? It is called Levy's continuity theorem. What is around 1920 something? Before, you see, before the all the setting of the setting of Kolmogorov, but didn't prevent mathematicians to do mathematics. So, okay, let Fn be a sequence of distribution function so this means that behind that you have probability measures, the same thing. Okay? And phi n be the sequence. I said mu is a probability measure. I defined what is the characteristic function of a measure. You can also define what is the characteristic function of the distribution function. It is the same thing to have a distribution function or to have a probability measure. So be the sequence, wouldn't like to spend all my time on that, of their, but I have to tell it, of their characteristic function, with the sequence of their characteristic function. Okay, then we have the following, and let f be a distribution function. So the distribution function of a probability measure. So if the sequence Fn converges weakly to f, point 1's convergence to each point where f is continuous, which is just to say that you have weak convergence also of the probability measures, then you have the following. The sequence phi n pointwise converges to phi. So let us say maybe phi associated to phi n and the characteristic function of the distribution f. So if you have weak convergence, this implies that you have pointwise convergence of the distribution function. Yes. So characteristic function, I should say also what is the characteristic function of a distribution function, and then it will be the same thing, because it is, then instead of saying d mu, it is even easier, because I would say it is d f mu. You can see it like that. Either you see it as a measure on R, or you see it as its characteristic, as its distribution function. It is exactly the same thing. In some way, you have a very clear one-to-one correspondence. Okay? And for the integral, you don't even know what is this, but you know what is the Riemann-Stieltjes integral associated to f. This is what it means. And so this means also that in some way what you have is that the mu n, which is associated to Fn, simply point 1's converge to mu. I start with the sequence of distribution function. And phi n is the sequence of their characteristic function.
So phi fn is that sequence. Is
Phi
it the
fn is the sequence of the characteristic function of fn. So, okay, you have, I think now we start to be a bit used to say that a distribution function or a probability measure, this is exactly the same thing.
This is actually generally called moment generating function in theory.
Sorry?
This characteristic function is actually called moment generating function.
It's called?
Moment generating function.
Okay, in any case, it is called also characteristic functions, whatever you like, because you may be more on the functional analysis side or on the probability side. Okay, but so this you have this point-one convergence. Now this is not that difficult, and this is not what is the most interesting. Now, what is interesting is that what happens if okay, so this is to say that if you have this, okay, you are fine. Now, what happens, you are up to that level. I don't know anything about the convergence, but I know that the sequence of phi n or phi fn converges to something. It's not exactly enough, but almost, and this is exactly what Levy's theorem will tell you. And this is the hard part. This is, in some way, this is the easy part. The hard part is the following, that if phi n simply converges, or phi fn as you wish, I could, okay, let me put a phi fn if you prefer, but okay. If phi fn simply converges to a function call it phi if you wish, but for the time being, I don't say that it is a characteristic function. Converges to a function phi which is continuous at 0, then you are on the good side. You know that phi is the characteristic function of a probability measure, and that the measure associated to the fn weakly converges to f. Then there exists phi, as you wish, the measure of the distribution function as you wish. There exists phi, a distribution function, such that phi is phi f, and your sequence of probability measure weakly converges to f. Should I repeat it? What is important is to understand what is in which order it goes. If you know that you have convergence, weak convergence of measures or of that distribution function, this is the same thing, then you have pointwise convergence of the Fourier transform of the characteristic functions.
So is that everywhere? This converges at every point, is it? Phi fn?
Sorry?
The characteristic functions converge at every point or simply?
Simply pointwise.
At every point, no continuity, nothing.
Yeah, at every point. Or everything is continuous. You are just integrating something which is continuous. It's not too difficult to. This is the easy part. Okay. If you just work a bit that you'll find it immediately. Well, what is the interesting part is that if you say that it simply converges, then it's not enough to ensure that you have indeed a convergence weak convergence of the measures they represent of the Fn. But there is something which is not too complicated to add, which is continuity at 0. If it converges with towards something which is continuous at 0, then you are happy. It is a good criterion to say that it will converge weakly. Of course, if it converges weakly, then it means that phi is phi f and
So in particular, if it continuous at a point, it is continuous everywhere.
sorry?
You are taking the converse question, right? You have a sequence of
Yeah. Yeah, okay. It is because I use simply, which is not good. Point-wise, yes.
the function phi f is continuous everywhere, right? The previous function.
Oh yes, the phi f are continuous everywhere.
Once you got continuity at 0, you got continuity everywhere.
Yes. Not only you get continuity everywhere, but you get the fact that it is indeed the Fourier transform of a measure, and that you have weak convergence toward this measure. Okay?
So why does continuity at 0 imply continuity at every point? Because
I know this is not obvious. I mean, I understand. I understand. This is not a trivial result. Levy's continuity theorem. This is the part which is easy, that you can do with your hands. You think a bit of that, and you'll think how it is. This is more difficult. Okay. So now we are back to what is for us of interest, which is arithmetic function. Corollary, which is what is of interest for us, and stop here this part, the following. So let f be a real arithmetic function. That is to say, a sequence, okay, of real numbers. Then f possesses a distribution function. There is a limit, which is a nice limit, a distribution function, if and only if the sequence of function t associate phi n of t. So we recognize this is the characteristic function which is associated to the empirical measure. So what is the empirical measure? It is 1 over n, summation f to n. And then what you do is to apply the Dirac function at the point f of n to that, to the function it. And so this is it of f of n. You remember this measure which was associated nu n of f, it is 1 over n, and then you put a Dirac measure at each point fn. Okay? So now if you have a Dirac measure at the point fn, what it is to integrate the function e to the I tx with respect to this measure, it's just to take the value at the point fn. That is to say, it is to do that. I'm not doing anything. This is just definitely this phi n is the phi n which is associated to the measure, empirical measure of the first n points. Okay, if and only if the sequence of function, I have not finished the sentence, pointwise converges towards a function which is continuous at 0. It's just reading Levy's theorem. It's just it's nothing. Towards a function phi which is continuous at 0, And of course, then phi is the characteristic function of the distribution, of the limiting distribution. Not only the limiting distribution exists, but you know what is this Fourier transform? It is this limit of the limiting distribution of f, which exists. So this is one way to see whether something exists. Look at the Fourier transform and see whether you have a pointwise convergence, and moreover that what you have at 0 is continuous, and then you are done. Okay? So this is a third point to see when you have this limit. Okay, good. I don't prove anything here, and I move to the maybe last part I wanted to say, which is the Erdős-Wintner. We already started to work a bit on that this morning, about Erdős-Wintner, which is what? Where is it? Here. 3,3. Okay, so last part here is Erdős-Wintner theorem. Okay, I start by quoting the following result of Kolmogorov. You have a probability theorem which is called Kolmogorov 3-series theorem. It says the following: let xn be a sequence of independent real random variable the series xn, summation of xn, converges almost surely So you know what it is. You have some probability space somewhere, okay? And so for each element little omega in this probability space, you know what is the meaning of xn of omega. It is a real number because you have real random variables. So when you have a family of real numbers, it makes sense to say whether the series converges or not. And to say almost surely, it means that the set of the little omega on which it converges is a subset of your huge, maybe, probability space, which has measure 1. Okay, this is what that means. Almost surely, if and only if there exists C positive such that the 3 following series converge. So now I tell you what are the 3 series. The one is that the probability that xn is larger than C This is each time you have a certain quantity, you have a random variable, you can measure how often it is larger than c. And of course, you expect that xn is not too large, usually. So this tells you that all the xn are not too large because the series of this converges. So it means at least that each term is tending to 0. This is at least what you have to ask, because if you are in a situation when you have too many omega on which your term doesn't tend to, xn doesn't tend to 0, there is no hope to expect that almost surely it will converge to 0. So in some way this makes sense. What makes sense also is that it shouldn't go too far apart. So it shouldn't go to infinity or to minus infinity or something like that. So what you expect also is that the expectation of xn, and then you may simply consider xn less than c. So that is to say that even if you look at what are the small values, in some way large values you have dealt with that. Large values, you don't have that many. Now we are concentrating on what is small value. Even for the small values, you want the expectation, the series of the expectation, to be convergent. Okay? Oh, okay. So this, what is the meaning of this random variable? Okay, xn times 1 xn less than c. You apply it to omega, leave some room because I will write a third series. Okay? I just want to tell you what it means. This, what is the value of that? The value of that is the following. This is real, all that, both are real valued functions on your or your big set omega. Okay? This is for omega. In omega, you have the following. When you take the value here, essentially will be xn. Well, it is xn if this is 1. And this, to mean that this is 1, it means that this quantity is less than c. So it is xn of omega if xn of omega is at most c. This is the 1 which is here, and otherwise it is 0. But in some way you don't care, you have already taken care of the large values here. This is a very strong assertion. This really tells you that essentially it is bounded by C, more or less. So you don't care now too much about the very large values. You see, the very large values may pollute your business here for the expectation, but you know in any case that there won't be that many. Okay? And also, sorry? Yeah, yes, the xn are independent.
No, what is the definition?
Of independent? Okay, I'll tell it later. Let me just finish the statement and I'll tell you what it means to be independent. Okay, and then what you want also is that the variance is not too large, they are somewhat concentrated. If they are not concentrated, you see that the sum can really go far apart. So you want also even, they are more and more squeezed when you are adding them. Okay? And so this is the summation of the variance of xn times the same thing. You have dealt with already the large values. You want this converges. So this is just to tell you what is the meaning of this. So the statement stops here. Okay? Statement stops here. It tells you have 3 series, and you are asking that the 3 series are almost surely convergent. That is to say that on a set of little omega of measure 1, those 3 series are convergent. Now now you have to say what is the meaning of random variables which are independent. Okay, fine. So you know some probability, you know what are independent events in a probability? Okay, so if you know that, it's okay, you know everything. So when you have a sequence an of events, you say that they are independent. Even if they are numerous, you don't care. Independent means the following, that for any I which is in n and which is finite, then you have the probability of the intersection of the AI when I belongs to I is the product of the probability of the AI. This, you take any finite sub-business and it's done. Well,
you need to add the subset of I also.
sorry?
Probability or intersection of any subset of I is optional.
No, for the time being, I am giving the definition. This is the definition of this family is independent.
So on I and also every subset of I, the probability of any subset.
No, for any I. No, if it is a subset of I, it is another I. What do you want to do? I don't know, a subset of something finite is another finite subset of n. I say for any finite subset, you have that. Of course, it is true also for, you may add some other finite subset, but you don't add anything if you do that. No, up to now, this is fine. Now, you have random variables. So random variables will do the following. You remember that when you have a random variable x, it is something which goes to omega to r. And we are saying the following in our understanding of it, that for any part in r, if you don't like it, call it measurable and then you are done. For any part of r, for any subset A in R, you are able to do something which is, we consider x minus 1 of A. X minus 1 of A, you remember it's what we were calling x belongs to A. That is to say, the set of all the omega for which I have omega, blah, 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 blah. So to this set, we know how to associate something which is, now this is in omega. This is a part in omega. And as a part in omega, I can look at its probability. Okay? So now what we are saying is the following, that your xn will be independent when you have the following, that when you take something which are all the elements that you can get from x, then they are independent. Okay? So this is the way you can see that your random variables are independent. That is to say that if they take some, the value they take, the reciprocal image are independent.
So you have this variance thing is actually that's series B, right, from the morning session?
Sorry?
So you have A, B and C.
Yes, this is.
So that is the B and this is the C, right?
Yes. Yeah, this is the way we did it here this morning, but I will say it now because we have to say it. This is A, B, C. Okay? But so now this is the probability context, and I'm not going to prove it, but it is definitely inspiration of Kolmogorov. We led Erdős, Wintner to do that, and Wintner was a probabilist. Let them to do the following. I'm going now to give you what is the Erdős-Wintner theorem. So the theorem of Erdős-Wintner is the following. Okay, so this is 1939. Tells you the following. Let f be a real additive function additive function. By the way, you may play some game and noticing that if it is true for some C, it is true for any C, exactly what we were doing this morning in the context of the Erdős-Wintner theorem. So this is why it may seem awkward, but if there exists one C positive for which it's true indeed for any positive C. So to prove it, choose just the C which is fine for you, but it's okay to use it. So it has a limiting distribution function. You see, it's a very strong result because it is if and only if. Okay? It has a limiting distribution function if and only if there exists some positive number, or you may call it C if you wish, such that the series, the following three series converge. So maybe I will put them in the same order as here. Summation 1 over p when f of p is larger than r. The second one will be the summation when f of p is at most r of f of p over p. And the third one is the square f of p squared divided by p when f of p is at most r. They are not positive, and we are not asking here for the absolute convergence. If it were absolute convergence, then there is no problem, because as soon as you have something like that and you know that this is true when f of p is small, then you get one from the other in some way. But this way they are not the same thing. So now there is something that you may think of is in some way, there is somewhere here something like independence. Where is the independence here? Is there something like some independence? Yes, additivity is very strong. Additivity tells you that indeed you have to know only what is going on for the prime 2, for the prime 3, and so on. And more or less to be divisible by 2 and to be divisible by 3 are independent events. And so this is why this will be independent on for all f. It is just enough. Now another remark also is that it is enough. You don't care about the powers. The powers play absolutely no role here. Okay, only, which again you may think it is something a bit curious, because you may think that well, square free numbers have not density 1. Okay, but it is in some way well understood. It which play each time on something which is like we enjoyed this property indeed yesterday, to have something which is convergent and to say it is enough to know at the sum of the primes when we have the inverse of primes, and for the other one we had something that was convergent like squares or something like that. We don't care much. Okay, what else? Well, convergence for any r, we say that. That depends. And of course, this will adapt. I have not finished the statement, but this is the basic part. Of course, if you have something which is a positive multiplicative function, then you have the same kind of result, because if you take the log, then it is an additive real function. And to say that they have distribution function, this is just the same thing, because log is an increasing function, or exponent is an increasing function. So to say that something is less, your multiplicative function is less than u, positive u, it will be the same thing as to say that the log of f is less than the log of u. So knowing what is the distribution function for a multiplicative function with positive values of a real additive function, this is exactly the same thing. And by the way, this morning we applied it to some multiplicative function. So there is something more that I will tell you. So this is very, very useful and very strong result. But in some way you can read it completely outside probability if you wish. There is no real probability in that. I show you something which is like probability when you look at Kolmogorov three-series theorem, but there's nothing like probability in that, except the word distribution function, but you can use it like that. So in this case, that is to say if they converge, I'm still in the statement of the theorem. In this case, the characteristic function of the limit law, of the limiting distribution of f, is phi of t, which is the product over the prime of 1 minus 1 over p, our old friend, times the summation when u is positive of something which is exponential of I t f of p nu divided by p nu. It bears some familiar taste in some way, this kind of thing. Now even for this you have something, maybe I don't write it even, or you may write it if you wish, which is to say that in this case the measure is pure. That is to say that either it is atomic or it is continuous but purely singular, or it is absolutely continuous. And it is continuous when you don't have too many elements which are equal to 0. So it is continuous. Maybe I don't say but the purity, but the continuity, moreover. This is in the power. This is in the power the same way, well, I have erased it, the same way I was saying what is the phi of the function. And of course you can explain it just in terms of the phi of p nu because it is something which is additive. Moreover, the limit law, the limiting distribution is continuous. This may be useful to know. Limiting distribution is continuous if you don't concentrate too much on 0. That is to say the sum, but it's not even the small values. You don't care about the small values. You want to simply to have something like that you have enough prime numbers on which f of p is different from 0. The limiting distribution is continuous, yes, if and only if. So this is very good tool for detecting whether you have a limiting distribution, and we didn't prove anything but tried to apply it. So, yeah, it's time to shift to additive business. I was thinking at first to speak only on the additive part. I know, because if you want to go into the detail of the additive part, it's also a complete mess. So, okay, let us move to this additive part where at least we'll see real probability, because we are building probabilistic model. So this is the last part, which is probability in additive number theory. additive functions is multiplicative number theory. Because what is important is that you have f of mn is equal to f of m plus f of n, but when mn are coprime, and this is definitely the multiplicative structure which is behind. Okay, this is something different. So maybe I should start with the random structure for one, if you wish, or something like that. I don't know. Random structures on subsets of n. Okay, so what we want to do now is the following, to say that you want to build, I said it in the very first lecture, what we want to do is, instead of saying, okay, this is my sequence of square, let me write it that way maybe. I don't know if it is good to write it into this, but make some little drawing maybe. So you have your integers, 1, 2, 3. Here you may put 0 or not, depends on your taste. This is not very important. And what you are saying each time is that, okay, if you have a set A, what is a subset A of n? Well, you are saying, for example, yes, colors are here. Okay. So we'll say, okay, 2 is in my set, 3 is in my set, 5 is in my set, 7 is in my set. You know which one is the next one. Okay, for example, this is the set of primes. Okay? So what you are doing, you are just selecting some element like that. Now you have another way to look at that, is to look at the indicator function. That is to say, instead of putting something at each level, you say it is in or it is not in. You say if it is in, I put a 1. If it is not in, I put a 0. Okay? So it will be the same thing again to look at your subset. Instead of looking at a subset, I looked at something which is 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, and so on. Okay? So this is now something which will be what I was describing before as something like a 1A. Okay? So in some way, this is deterministic. I have my sequence A and I know what it is. Okay. Now you have something else, which is you can do the following. Then it has in some way nothing to do with that. Let us put it like that. I start again with something which is 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. And what I do each time is above each integer, I put a random variable. So I put a function. It's not just a value, it's a function. Well, you may see always this as being a constant function in some way. You put something which will be always 1. It is the constant function. It is a function which 2, 3 always associated the value 1 with a constant function. But now I want to see a function which may take the value 0 or 1. So I will have here now something which are x0, x1. Maybe x is not that great because I put too many cross up to now. So let us say this will be zeta0, this will be zeta1, zeta2. I will come back, of course, to x later, but zeta4, blah, blah, blah. Those are random variables. Random variables, which are Bernoulli random variables, that is to say that psi n is something which goes from a huge probability set to values 0, 1. So each time I select a little omega in my set, capital omega, so for the time being it has nothing to do like that, but select a little omega. Then you can figure out what is zeta 0 of omega, zeta 1 of omega, blah, 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 zeta 4 of omega, and so on. But this is a sequence of 0 and 1, because we are just looking at Bernoulli random variables. This is a set of 0 and 1. So as a set of 0 and 1, I can consider that as being the indicator function of some set. Okay? So I will read that, this sequence, I will read it as 1 a omega, which take the values 0 and 1. So above that, in some way, I have a sequence a omega. Each time it is equal to 1. If this is equal to 1, I put a cross. And if this one is equal to 0, I put nothing. Okay? So what we are doing is the following. As soon as we have function, they need not be even random variables. Random variable is just a function. Each time you have a function and a big set with value in 0, 1, to each element in this set, you can associate a subsequence of A, which is the sequence where you have all the value which are 1. You just select the value 1.
Then what is the parameter later? How do you define the probability of success?
This is for the time being what I say is that we are replacing in some way the value which is just always 1 or 0 by something which will depend because it depends on a function. Okay, good. So now you are right. You want to say what we can associate to that. Now, knowing that what you have are random variables, you can associate to each n something which will be the probability that xn is equal to 1, or the probability that xn is equal to 0. Moreover, if you want to do something about that, of course, if you have, you may have about random variables, maybe constant random variables. That is to say, the probability that xn, for example, the probability, if I take the probability that x2 is equal to 1, we'll always get a 1, almost always. The probability that x3 is equal to 1, I get a 1 almost always. This is not of real interest. It will be more or less the same thing as saying that. Each time that I have my random variable is xp, when p is a prime, I say, well, the value will be always 1. The probability that it is 1 is equal to 1. The probability that, yes, it is equal to 1 is 1. This is not very interesting. But you may say, okay, I select them more or less randomly. Okay? So what we can do is the following. So now we understand that what is important is to have a sequence of random variable of function. For the time being, forget even that we can measure them. You are right. Soon we'll measure them. We consider them as being just function. We have a family of function from a certain set omega to 0, 1. And then to each element of my set, capital omega, I can associate a sequence. Okay? So now what we are going to do is to say, okay, what we would like to have is, in some way, if we want to be able to say something, essentially we are going to select them independently. Okay? Well, we see what we can do. You may also say that you want that they are not independent. For example, you want to say that I want a sequence such that each time one element is in my sequence, the two neighbors are not. This is also something. So it is, they are no longer independent. You need not put them independent. Okay? But for the time being, let us start with something which is independent. But you can build also a model in which they are not. Okay? And what will be important for you is to know what is the probability that you get a 1, what is the probability that you get something like that. So for example, if you want to say, I would like to have something which looks like prime numbers, what will be the probability to take n? That in this, the probability that psi n is equal to 1. If you are thinking that you want something like prime numbers, you say, okay, what is the probability that the number n, or of course, if you give a one number, it is a prime or it is not. But if you select more or less randomly something around n, what is the probability when you go randomly to get a prime number? This probability is about 1 over log n. Okay, this is the prime number theorem. Essentially, prime number theorem is telling you that. So what is important is to have this probability, which is, let us say, 1 over log n. So you are going to say, now you are using the fact that they are random variable, and you are saying that. Now you see that if you don't put something which is more or less random, you may say, okay, maybe the probability is 1 over n, but if you force each time that one element is in, all the neighbors are in, you don't have really something which is a good model for prime numbers. Okay, if you want to have a good model for prime numbers, better you assume that they are independent. Now you may say, okay, but this is not exactly the real life of prime numbers, because prime numbers, if you have one which is a prime, the neighbor is not. Forget about this counter example. But beside that, if one is a prime, the other is not. So you see, you have room for building models according to what you want to do. But the simpler model we are going to work with a model in which you simply say, okay, they are independent. You select them with something like 1 over n, 1 over log n, and they are independent. And then you can show, for example, first that they behave, you have a prime number theorem almost surely. For almost all omega, you will get something which is the number of elements up to x will be x over log x. Okay? So now I would like to put the random structure on subset of n directly. You have some understanding of what we are doing. What we are doing is to say for each n, we're just selecting in some way the fact that n belongs to my sequence or not. I will do that randomly. Okay? And randomly, and better if you don't have something which is independent, you may be really in difficulty. You need to have some sort of independence. By the way, the good models for prime numbers are done that way.
So then one can model these few conjecture, like two-step conjecture or the other Goldberg conjecture like this.
Yes. So then you say, okay, then of course, then we are going to do something which is additive number theory. So we don't know that every integer is the sum of two primes. But you say, okay, we select something like that, so we have some random sequence. Is it true that when we add this random sequence with itself, is it true that almost surely every element is a sum of two primes? And then you feel a bit better if you say, yes, we can prove that almost surely it is like that. And then you try to see whether it looks like what you are used to in the real life. So let me now give some sort of definition. First of all, there is something which is just some existence theorem that if you want to have this type of random variables which are independent and so on, it is possible to build a large set omega on which it is true. Okay? So let us put this theorem for the sake of precision. So, okay, we consider P1, P2, Pn, blah, 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 numbers in 0, 1. So there will be the probability that xn is equal to 1. Okay? So, okay, then what we say that there exists a probability space let us say omega sp, or I put tau, let us keep the same notation, and a map from omega to p of n such that you see my map associates to any element a sequence. This is what we want to do here. For each omega, we are associated something which is the map, the set which is here. Okay? So that we have the following. First condition is that for any n, the set of omega such that n belongs to omega, a omega, is indeed something which is measurable. Put it a omega if you wish, belongs to S. Okay, this is fine. You see, we were saying if we are on R, if tau, this one. You see, if we're on R, we say, okay, everything is measurable. If we're on any large set, you may have difficulties. Solver doesn't work like that. Okay, but this is not the real part. This you forget about that immediately. Okay, this is not important. What is important is that the P of n belongs to A, omega belongs to A. That is to say, the set of omega such that n belongs to A of omega. Always with the nice oranges, you know. This means the probability of the set of omega such that n belongs to A of omega. This is the oranges which are sold here. And we want this to be equal to Pn. Okay? And now what is important is that when you are looking at the events, one belongs to A. Again, you understand what it means. So you have a family of events. This is the pullback. That is to say, you are looking at the set of omega for which one in the sequence A of omega. Okay, so this is something which lies in capital omega. Indeed, they lie even in tau. So there are these events, and what you are saying is that these events are independent. And it's possible to build a large model on which it's true. So we don't care much. We are going to say, okay, the model exists. Let us work on that. Are independent. You see, so this means that, for example, if you take for Pn something which is 1 over log n, forget about n is equal to 1, you put whatever you wish, but you get something which looks like primes. Immediately in this model, you are saying that it is quite possible that n is a prime and n plus 1 is a prime. This will occur with the probability 1 over log n plus 1, okay, which you know it's not really the real life. So if you want to work with the real life, you'll do something a bit different. Same thing for squares. If you want to get a model for squares, we'll see what are the Pn which will lead to a model for squares. But in some way, in this model for squares, we are going to say that the probability that n and n plus 1 are both squares is something that is non-zero. Okay. Well, you may like it or not, and we built indeed some more realistic arithmetic model, but already this is in this modeling you are able to say a few things like that. Okay. So okay, notation maybe. Do I need that? Maybe not. Yes, because this will be useful all the time. Okay, so what we have to do is to say when you have n and omega, notation. I initially put something which was a delta, but this is not good because we have too many delta. It has something which values 0 and 1, but I prefer to put it in another way. So for n, for any n natural integer, we let a function kn, which is a function from omega to, did I say something? Yeah, from omega to 0, 1. This will be in some way the this is the random variable that you have. When you have n, you say whether you are in the business or not, which is defined in the following way, that kn of omega is equal to 1 if n belongs to a of omega and 0 otherwise. Let us say if n does not belong to a of omega. So this is a random variable because it is a set which is defined. Well, you have to see that the reciprocal image of that is equal to is in tau, and this is ensured by that. So kn of omega is this. So in some way, what we are doing is that what I am saying is that each time I've tossed the coin or I've thrown the dice, that is to say, you choose little omega. All the values are well known. You know whether it is in or not. And each time n is in your sequence, you put a 1 at the value n or 0. And so this is a nice random variable. So in some way, what I am saying is the following, that kn of omega is the same thing as the indicator function of a of omega at the point n. Sort of dual function of that. Okay? So what is, for example, just to give some idea, how many terms, baby exercise, how many integers up to capital N are in A omega? The counting function. See, it is quite important to have the counting function if you want to do something. To add integers, something like that, you want to know how it behaves, so it's very important to have the counting function. So this counting function, A omega n, which is the cardinality of n up to capital N, so that n belongs to A of omega. There is a curly A and a capital A for the counting function and for the set. This is a set. So omega is given. And for n, I want to count this number. How can I express it? You see that what we are doing is to say that this is the sum when n is up to capital N of k of omega, kn of omega. So if you forget about the omega, and more or less we are going to say, okay, I have a random set, I will call it A. I don't make reference to omega. I have a random set, and I know how many terms do I have up to n. Well, the number of terms I have up to m will be the sum of the random variables kn. So you have sum of random variables, and you have at least something you can start to work on because you have assumed that those random variables are independent. This is exactly what it is said here. The condition 2 tells you that the random variables kn are independent. Okay, notice that 2 means that the random variables kn are independent. Kappa n or kn, as you wish, are independent. So we're dealing with sum of random variables. Independent random variables were in a good probabilistic context. Time for the snack? Yeah, I think it's good because it needs some time to understand what we are doing when we are saying this is a random set. Okay, if you are not used to that, it will take some time, so think a bit of that before tomorrow. What is a random set?